Okay, I want to show you the math now for discharging capacitors. Sometimes these are called RC circuits because they have both a resistance and a capacitance, and so that's called an RC circuit. Okay, so here's how the math goes. It's just applying Kirchhoff's loop rule. And so if we have a capacitor and a resistor, see the RC circuit, and let's charge that up. And let's call this Q naught. Let's call that C, and this is R. Q naught is the original charge on the capacitor. Now when you close this switch, before you close this switch, all the voltage drop has to be across the switch because there's no current in here. This still has some voltage though. Here's the electric field in here. So if I go up some, I got to come down some voltage. Okay. Now when I close this switch, then the charge is going to swoop around. We're going to call charge, we've been calling charge the flow of positive charge. That's the conventional way of, that's called conventional current, the flow of positive charge. Even though it's electrons that are going this way, we've been calling charge current the flow of positive charge. So I'm going to say that the current goes this way. All right, so when you do that, then what happens is the charge, these electrons, they want to leave here. And at first, they want to leave real fast because there's a lot of them and there's a lot of positive charges over there. So they zip on over. But as time goes on, there's less here pushing each other away. And there's less of these guys attracting. And so the electrons take their time a lot. They're a lot slower at getting over as time goes on. Think of it this way. The charge here is the biggest at the beginning, and so the voltage is the biggest at the beginning. And so this voltage is the biggest at the beginning. As time goes on, when this has less charge, this has less voltage, this has less voltage, this has less current. All right, well, I'm just going to do a Kirchhoff's loop rule. I'm going to say that the voltage across the capacitor plus the voltage across the resistor has to equal 0. Now the voltage across the capacitor is Q over C. I'm calling Q, I'm going to remind you that this charge is the charge on the capacitor, so I'll call it Q sub C, though I'm going to drop that C in the next line or two. Okay, so that's Q over C, that's the voltage across the capacitor. Okay, and then so if you start here, you go up that much, Q over C, and then you're going to come down, I times R. Now notice I made the I lowercase, and I made it lowercase because that I is going to change with time. So that's a variable, constant. That's a constant. Variable, constant. These will change. These won't change. All right, so here goes. So I'm gonna replace this I with dq dt. So Q sub C over C minus, now this is dq dt. But if I'm going to have it be the Q on the capacitor with time, how it changes with time, that's related to the current through here. Then it being dq dt, I want you to see something here. Let me just complete this. Times R is equal to 0. So the voltage across capacitor, this is the I, but now it's really not the I, because you see how the charge is depleting with time? The charge is getting less and less with time. So this is going to be a negative quantity. And I want the I to be positive. And so since the rate at which this is changing with time, it's decreasing with time, I'm going to put another negative there so that it makes the I positive. All right, so let me do the next line here. It's going to be Q over C minus, or how about I bring all this stuff to the other side? So that's a plus, and when I bring it to the other side, it's going to be a negative dq dt times R, and that'll be negative. Okay, I'd like to get my terms together, and so Q, which is the variable, I'd like it on the same side as dq, and then the dt I'll bring over to the other side. And so in the R and the C, maybe I'll get together too. So I'll bring the R over here as well. So coming over here, I'm going to have, let's see, dt negative dt over RC, that's equal to dq over q. Did that work out for you? See how that works? Okay, then I'm going to integrate both sides. So I'm going to integrate this negative dt over RC, and I'm going to integrate this too. And let me get my boundary conditions. So I want it to start at t equals 0, and I'd like it to go to some other time t. And so this should start at q naught. These always got to correspond. So at time t equals 0, q has to be q naught, and then at some other time t, this will be some lowercase q. All right, let's just do the math. Doing the math. Let's bring this over here. So I'm thinking that on this side, that you can pull the negative RC out, and when you integrate that, that's just going to go to t over RC, negative t over RC. That's what that goes to when you put in your 0 and your t. On this side, you get the natural log of q minus the natural log of q naught when you put in your boundary conditions. Okay, we can combine these and say this is the same thing as t over RC, negative, is equal to the natural log of q over q naught. All right, we'd like to get q all alone, little q all alone. And so maybe what I'll do is, since this is equal to this, then e raised to this has to equal e raised to that. So and so what happens then is this can be reduced to just q over q naught. And this is going to be e to the negative t over RC. So q apparently is q naught times e to the negative t over RC. So by doing that, we were able to get the constant. The constant that I called k in the last video is 1 over RC. That's what the constant is. It's 1 over RC. All right, if I were to graph this then, how the charge changes with time, apparently it starts at q naught and it decays. And look, these are in the denominator, so it looks like, remember, whenever the constant in front of the t, whenever that's big, it decays fast. So that means that if r is big and c is big, that means that it's going to, the bigger these two are, the less time, the longer it's going to take to decay. So like if I shorten both of these up, if I made these really small, r and c both really small, what happens is the constant actually gets really big, and so it decays faster. And why should that be? Well, think about it. If you make r really tiny, then the charge doesn't have any resistance getting through. Okay, so that's just, and if you make c really small, then and you have the same charge, making c really small, then they're really packed in there. C's really small, and you give them a chance to get away, and they're going to get away as fast as they can. One other thing then, if that's q, getting I is no problem, or any of the other ones for that circuit. So if q equals q naught e to the negative t over RC, then just I is going to be the negative derivative of q with respect to time. And so that's going to be, when I take the negative derivative of that with respect to time, I get q naught over RC e to the negative t over RC. Hey, look, that's voltage. Or excuse me, that's current. That's a voltage divided by R. All right, thanks. Bye.